Thank you very much. It's actually quite nice for me to be the last speaker because most of the speakers before cover a lot of the concepts that I will mention during the talk, so I don't have to spend too much time on it. At the same time, I really appreciated the honesty of the speakers before, where they came on stage and they said, look, today there will be more questions and more challenges than answers. And it is really nice, right? And that kind of connects to this whole idea of hope and despair in a time of quantum computation. So the reality is that a lot has happened in the field in the last few years, actually. But we still have so much, really so much to do before we can say that the field is fully mature and we're actually using quantum computers for something non-trivial and something useful. So hope is because of the advancements. And hope also connects to my own personal story of moving from a postdoc position in academia to try to launch a startup in Singapore and take quantum computing and do something useful and financially valuable with it. Despair, because we still don't really know what's happening in the next 5 years. You might have realized from the previous talks that there is this big gap between what the theory tells us that we can do with quantum computers and what we actually have today. And in between, there is this uncharted territory where we don't really know what can happen, which is amazing because it gives a lot of opportunities, but it can also be a little scary. Okay, so this is the agenda for the talk today. Just a word of warning, there won't be really too many technical details here. This is also the last talk, so I try to keep it a little more, engaging and simple. I will try to give you the perspective from, more of a business perspective, if you like, of the field. I will also share insights, my personal insights, what I think is going to happen, how we think at Entropica we can actually do something useful with the machines that we have and we are going to have in the near future. So I'll start with the quantum landscape, what is actually happening around the world in the field. Then a few thoughts on quantum computing, how I really like to think about this whole idea of quantum computation. Technicalities, so a little bit of technical details. Especially you heard about this concept of variational quantum algorithms before by Anh He from IBM, and also how these ideas connect to unsupervised learning. And again, I will really try what I can to connect to what the speakers were saying before, so to bring everything in a bit of a cohesive way to close the symposium. Then I will conclude what is next. Hope. Should we be really hopeful, really happy? I think we should. Or despair. Okay, so the quantum landscape. I think it's quite interesting that in a place very small like Singapore, actually, if you compare it, for example, with the US or with China, it's a very small country with a rather small population. Well, first of all, we have CQT. It's really acting as a magnet to bring together all the talents in the field. But at the same time, there are today already 3 spin-offs on quantum computing coming from CQT. So we are one of them, Entropica. I will talk a little bit more about us in a second. Then you have Horizon Quantum Computing, which was launched by Professor Fitzsimons from SUTD and CQT, which is where I used to work before doing Entropica, and Innovatus Q. So Horizon and Entropica are focusing on the software side of things, while Innovatus Q is focusing on the hardware, so on actually building processors. As I mentioned, they're all spin-offs of CQT, and again, I really want to emphasize how quite amazing actually is the fact that we have already a very interesting, very thriving ecosystem here in Singapore. So a little bit of, I'll just say a few words about us. So the founding team is myself. As I mentioned, I used to work with Joe at SUTD and CQT. I was working on blind quantum computing mostly, and Yuan, who was a PhD at CQT with Professor Kwek. So what we did, exactly a year ago actually, we started an incubator program, and the motivation for doing that was really to take the technology, quantum computing, and do something useful with it. Where useful means not only useful for people, also useful for us, meaning financially valuable. So what is the idea of Entropica? Basically, what we are building are advanced computing tools. As you might have noticed, I'm on purpose not using quantum computing tools, because I think one has to be very realistic and really admit that classical computing is extremely powerful. And there is a long way to go for quantum to reach that level of power. And the application is molecular biology. There is this beautiful idea in molecular biology that if you want to understand complex diseases, and cancer, unfortunately, is a very well-known one, you should not limit yourself to look at a single specific genetic cause or molecular cause, but instead try to map the whole system to a network and analyze what happens at the interaction level. This is computationally very hard to do. I can see a lot of potential for quantum computing eventually to play a major role in the pipeline, so maybe we can discuss more about that later. But the idea is really there. Make sense of complex systems, of complex diseases by looking at the whole set of interactions. So we have a team of 3. Joaquin and Jan Lucas are actually here at the symposium, so later you might want to go and talk to them. Joaquin is an expert in distributed computing, which is also something that sometimes we forget as quantum computing theorists, that again, there is a lot of power in classical computing, and maybe we can make good use of it, even in quantum. Jan Lucas is doing an internship with us. Today I would say, is an expert in QAOA, which is an algorithm that has been mentioned before, and I will talk a little bit more about it later. So if you're interested about variational algorithms, you should certainly talk to him. While Amar, who's in Canada, in Toronto, is an MBA student and is working with us for the business development. Okay, so let's look at what is actually happening on the planet. I guess all of you have seen these names before, and this is really, first of all, these are not all the players in the hardware scene of quantum computing, but most of them. It's quite nice to look at this picture because you can really see that there are clusters starting to create worldwide, and it also means that there's a lot of competition. And especially when you have competitions between big countries, that is usually a good thing at the technological level because it means more money to the technology, especially because quantum computing could have applications at the military level, which is really pushing the field forward. To give you another idea, it's quite interesting that D-Wave up to today raised slightly more than 200 million in funds over almost 20 years' time. And then just a few months ago, Alibaba committed $15 billion for quantum computing, which is really, if you like, very different scale of funds. Again, good, and then hopefully there is a comeback from this side of the world. Positive. Competition is always a good thing. We want that. I mean, Patrick already showed you a graph very similar to this one. You get the idea. It was very nice to hear about the quantum volume by IBM. Of course, the number of qubits is not the only thing that matters, but is a very important one. If we don't have qubits, then everything else kind of doesn't matter too much. And if you look at what has been happening in the last 2.5 years, well, the number of qubits has been growing pretty fast. It's a little hard to extrapolate law because we don't have so many data points, and it's also difficult to say exactly when the qubits have been built, whether it's the announcement date or whatever. But you could say that the number of qubits has been doubling between 6 to 9 months, which is faster than Moore's law. Is it going to last? Hard to say. But at least up to now, it's very positive to see that trend. I think what is even more interesting is this whole idea of quantum computing on the cloud. So I'll explain the graph in a second, but just to illustrate the concept. So the big blue circle is the cloud, which means right now you can take your laptop and connect to it quite easily. Well, 10 years ago, that was empty. There was nothing in there. It was maybe more of a hope. But today, you can start to see that it's quite populated. So let me explain you what this means. Basically, the red square here are the companies that are using a gate-based discrete variables approach, okay? The one that I guess most of us are familiar with. Then here on the blue one, you have gate-based continuous variables approach and quantum annealing on the top right corner. Then there is another distinction, which I think is very important to do. On the upper part of the screen, you have all the physical devices. Devices are actually, I'm going to say, real quantum computers, meaning that they actually have a quantum chip, or at least something that should behave like a quantum chip. While on the lower corner, you have companies that are still offering a simulated quantum experience. The hardware is not there yet, but you can use something that looks and feels like a quantum computer without being a real device. Okay? So after that, I would like to speak a little bit about the startup scene, and I want to introduce that with this quite funny cartoon, actually. I'll give you 5 seconds to read it. Certainly applies for us too. Like, the reality is that we all think it could work for us, but sometimes we're also a little bit skeptical of what the other people are doing. Again, that might be a good thing. And just to give you an idea, this graph was done by actually Alba, who's a PhD student in Barcelona. So together with her, Yuan and myself write articles for the Quantum World Association. And here, again, this is just a representative list of players, so not everyone is there. This was done a few months ago. I think it was September or October, so just very recently. And the funny thing is that even just in these few months, some of the companies have already changed logos. For example, us. We didn't even have a logo at the time, so there was just our name. Zapata, which is certainly a better representative of the, of the software startup scene, they have a different logo today. Some of the companies don't already exist anymore. So things are moving really fast, extremely fast. Again, that's very nice. It means that there is a real interest, not only from the scientists, but also from the business people, also from people who might have very strong technical expertise, even if they don't come from the quantum community, to try to do something out of it. Of course, there's also a lot of hype, which is a bad and a good thing. But very interesting, very, very active ecosystem, a lot of good ideas coming out of that. Okay, so a few thoughts of quantum computing. How should we think about quantum computing? First of all, let's start with a few questions. The first one is that most known quantum algorithms have resource requirements that are way beyond what we can actually do today. This concept has been mentioned a few times today, and there's really this idea that, for example, if we have fault-tolerant quantum computer with 10,000 logical qubits, then we can do HHL, the matrix inversion algorithm. But we don't have that, and maybe we won't have that for 10, 15, or 20 years. Okay, it's good to keep that in mind. What I think is very important is that we need practical applications. If we want to build a business out of that, we certainly do. Practical applications here, what I mean is in the near term. Because even in the long term, everyone knows Shor algorithm, but I believe it's very hard to make a case for Shor algorithm of being actually useful for anything beyond the strong scientific value of it and the potential disruption for the cryptography. You can't really build a business out of that. Well, depends, but in theory, it would be a little hard. Another ingredient that I believe is very important for the field is more crosstalk between disciplines. At the beginning, you've seen that we are now working on molecular biology, which is not really our background. What is extremely interesting is that when you go to speak to the experts of the field, they have a lot of questions that are very similar to ours. And for me, it was very fascinating to see that, which means they also have needs that are very similar to ours. And then when you talk to them, you start to understand exactly where we should focus. That's very nice. But we need more of that. So a fair prediction, I believe most of the speakers today have said that, but I repeat it again. In the near term, quantum processors will have few hundred, maybe 1,000 qubits. And there will be no error correction, so noise. Just a lot of noise in the circuits. Can we do something useful with that? I believe we can. But there's not really a strong proof for that. There is some evidence, there are some indications, but we don't really know that yet. All right. So how to think of what I call quantum-enhanced computing techniques? I really like this way of thinking, and this is something that was developed by talking to colleagues, and also when you try to go and give a talk to the public who might not have a strong background in quantum computing, how do you actually explain these concepts without going back to the idea of qubit and entanglement? Try to think about it a little differently. Okay, let's start with these architectures. You might know what they are. They're all classical information processors. Okay? What they do, they basically change the state of a long sequence of bits. They do digital operations. They can do it very fast. They can perform deterministic operations really, really quickly. And most importantly, they are extremely good, especially these guys, to perform parallelizable computations. Extremely good. I mean, the great success of deep neural networks is because of that. You can take the computation, parallelize it across many devices, and get an immense speed up. Fine. How should we think of quantum processors? Well, we know that quantum mechanics is intrinsically probabilistic, right? And this is the very first big difference. Now, we should start thinking about probability distributions. Okay? So a quantum processor is something that can process a probability distribution, loosely speaking. But there is another very important difference. I think the way we should, the kind of problems that we should think for quantum computers are problems that are intrinsically hard or impossible to parallelize, problems that you need to look at globally to make sense of them. And we're not really used to think about those kind of problems, especially today with the great successes of machine learning, because we tend to stick with problems that are parallelizable, supervised, which means, as Patrick mentioned before, you try to, for example, distinguish between a picture whether it's a cat or a dog. And you have a lot of pictures before to do the training, so the machine learns how to do that separation and then does it for you. And these kind of problems are also discriminative. As the example I just mentioned, they're going to tell you, yeah, it's a cat. Going back to this idea of probabilities and global calculations, maybe especially looking at machine learning, the kind of problems that I think we should really be focused on are problems that are unsupervised, which are intrinsically very hard on classical machines and are starting to gain some traction now, and also generative. What do I mean by generative models? So generative models are models that instead of giving you a label at the end, 0, 1, cat, dog, they give you a probability distribution. And then you can sample the probability distribution to understand something about the system that you're looking at. Okay? These are intrinsically hard on classical machines. I'm not making a claim that quantum processors will magically solve them, but they seem to have the right structure for this paradigm. And I think we should keep that in mind. And maybe I'll push myself a little, beyond what I wanted to say and say, deep neural networks are not good applications for quantum computers because we can do it extremely well with what we have already. And before we reach a level where we can use quantum processors for it, it's going to take a very, very long time. Let's try to think a little bit differently about quantum processors. All right. Another important point that has been mentioned today, but I really want to emphasize it again, is that quantum computers don't live by themselves. The right way today, at least, to think about quantum processors is really of these hybrid classical quantum systems and also algorithms. You have a classical computer that controls the quantum architectures and just delegates a small part of the computation to the QPU, the quantum processing unit. And this fancy graph is just a way to say that there is a lot of noise acting on it, which means that you need control from the CPU to basically drive the behavior of the QPU. It's also very important to keep that in mind. This is the kind of architecture that we are going to have to play with for, I guess, the next 3 to 5 years. Okay, so some technicalities. What do I think we can do in the short term with these machines? First of all, we need to keep in mind a few points. So the green ones are the hopes, the good things, and the red ones are the despair, the bad things. First of all, we might have hundreds of qubits available soon. That's fantastic. And with them, going back to what Mick was saying about these random circuits, we can produce states that are so large in their Hilbert space that even just trying to store them in classical memories becomes impossible. Okay? We shouldn't extrapolate too much from that sentence. Just keep in mind that we can do something which is highly non-trivial for classical machines. The bad things are that the qubits are noisy, and we need to keep that in mind. There's no error correction available, so we have to deal with the noise somehow, or at least live with it. And the circuit depth is very, very short. So whatever we want to do needs to happen in a very short circuit size. Also interesting is that, there's not a single way, we don't only have one way to build a quantum computer, but there are different architectures. And these architectures have interactions that might be intrinsically different. Can we exploit that somehow? If you put all these ingredients together, then you come up with this very nice idea of variational quantum algorithms. Again, as you can see, it's an hybrid system, so you have CPUs and QPUs working together. And what you're trying to do, you're trying to minimize a cost function. And the cost function in this case is the energy of an Hamiltonian. So you can think of the cost function as your Hamiltonian HQ, and you're trying to minimize the energy of that. You want to find the ground state associated to the lowest energy. This is a very simplistic way to think about it, but it kind of gives away the whole idea. You start with a set of classical parameters produced by your classical computer. You feed it to the quantum machine, you prepare a quantum state, and then you measure the energy. You take the energy, you feed it back to the CPU, and with that energy and the initial set of parameters, you produce a second set of parameters, and you repeat, and you repeat, and you repeat, until you find an energy which is low enough, or at least until you don't see any other improvement. So this idea was introduced by Alberto Peruzzo and collaborators in 2013. So it's quite recent, actually. And it can be very powerful because, as was shown by Anhi before, you need a very short circuit, and this seems to be quite resilient to noise. So that's really great. Let's look at a particular case, is the QAOA, which I mentioned at the beginning, the quantum approximate optimization algorithm. What you're doing here, you are encoding inside the Hamiltonian, the cost Hamiltonian, a classical optimization system. So the example you have seen before with the energy of the ground state of a molecule, you're doing something different. You're encoding fermionic Hamiltonian into this HQ. Here you're looking at a classical optimization system. A very nice example of that is an unsupervised machine learning problem. It's clustering, and it's called MaxCut, which turns out is actually NP-complete, so it's hard. It's not a friendly problem for classical computers. What you want to do, you have a graph, and you want to basically cluster the nodes in two sets so that you maximize the cuts between the two sets. For this very simple example, this is a solution with 5 cuts, which, if I've done it correctly, is one of the best solutions. It's not the only one. It's usually highly symmetric. So you have a degeneracy in the ground state. And this idea of QAOA, which is a subset of variational algorithms, was introduced by Fari and, in 2014. Nice. OK. Rigetti, in 2017, so just a bit more than a year ago, actually took this idea and tested it on their device. To give you a bit more intuition of what QAOA really does, is related to the quantum adiabatic algorithm. So you want to imagine this is your target cost Hamiltonian, and you want to find the ground state of the Hamiltonian. But it's hard to do on a classical computer, ideally. So what you do, you start from a simple Hamiltonian, and you know the ground state of that. And you adiabatically move from one to the other, slowly, slowly. And the adiabatic theorem tells you that you should reach the ground state if you start from the ground state. On a gate quantum computer, on a gate-based quantum computer, you can't really do that. So what you do, you discretize that path. And in QAOA, you start with, it basically gives you an ansatz on how to do the discretization. And instead of taking many, many short paths, which would be the ideal case, but you can't really do that because you need a very long circuit depth to do it. So you have to use a short circuit depth instead. You take these big jumps, boom, 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 and you try to get very close to your target. So maybe the first time you end up quite off. So you optimize with a classical machine, and you try a second time, and maybe you get a little closer. And then you try a third time, and you get even closer, et cetera, till you reach, some good boundary of your target Hamiltonian. Oh, OK. So Rigetti did that on their 19-qubit system. They showed that this actually can work. Of course, this is not quantum advantage or not even close to that, but they just showed that this can actually work. Another use case was suggested by the team of Xanadu, and if I'm not wrong, Patrick was one of the authors in one of the papers. And the idea is, again, this idea of global computations. Here, what they want to do, they want to find basically, you have a graph, and you want to find the k-dense subgraph, which means a subgraph of k vertices that is the most dense among all the possible subgraphs. It is also quite hard to do on a classical computer. It's actually NP hard in the worst case. And while they haven't tested it on a real quantum device, because they're still working on it, their proposal is to use a Gaussian boson sampler, which goes back to the kind of machineries that Mick was talking before. They're not universal, but they're supposed to do something better than classical machines. And here they suggested to use it to basically enhance classical stochastic algorithms for this problem. So it is very nice. We really start to see that maybe something is possible, even with small devices. We can do something non-trivial the classical computers struggle to solve. OK, so what is next? I've been told a few minutes left, so I'll go a little bit faster here. What to expect in the next years, the first thing will be a demonstration of quantum advantage. Has been said a lot about it today, so I won't focus too much. But I think what is very, very interesting is this back and forth between classical and quantum computation. So keep in mind, the people who have been working on classical computing are really damn smart. And they've been working on these problems for way longer than we have. So if we want to beat them, we really need to be super smart. a good outcome of that is that we can learn from the architecture of quantum circuits. Even if they don't give an advantage on the quantum computer, we can learn something about the structure of these circuits and go back and run them on the classical machines and still get improvements over what we can do today. So these are not like quantum-inspired classical algorithms. There is already an amazing outcome, because at the end of the day, the only thing that really matters is whether we can solve the problems or not. It is not so important what technology we use. Second point is that we are going to have several 100 qubits available. And I just want to make one point here, which I think is very interesting. Something that happened in classical computing that sometimes is not really fully appreciated is that we started to build better classical computers, and we used those to build even better classical computers. This is one of the reasons like why we had the Moore's law, because we had more computing power to keep on pushing it. So the same can certainly happen for quantum computers. We use them to understand what happens in a quantum computer so that we can build a better one. And that could really help to speed up the whole process of improvement in quantum. The last point is more focused on quantum software and rollout to the world. The reality is that that is pretty much all missing. And it's really necessary to work on that at the side of the hardware effort and also algorithmic effort. So do we have enough provisions to survive a quantum winter? Maybe. We certainly have more money, more qubits, less errors. We have very powerful classical simulators, which can be very useful as well. And it seems to me that quantum-enhanced machine learning could be a very good application for near term. Why? Because it works. We haven't really proven, this is a conversation I was having with Joaquin just before the talk, it works. We don't have quantum advantage yet, but we can do something which is non-trivial, which means we are going in the right direction. We have the hype. Hype can be very good because it usually means more money and more interest. On the other hand, we still don't know if near-term algorithms can fare any better than classical ones. That remains to be seen. As I said a few times, classical computers are very powerful, and if we want to beat them, we need to do way more. Fault tolerance is still decades away, and Wei-Kun spoke a lot about it. Going back to this idea of software architectures, we really don't have debuggers. We don't have good ideas for how to debug a quantum computation. How do you debug something that you can't really observe until the end of the computation? What about quantum random access memory is another huge hardware problem? Or even just data structures. How do we think about data structures on quantum computation? In classical, we kind of give it for granted, but there was a lot of work done to specify very precise data structures in classical computing. Maybe something like that needs to be done in quantum as well. And we have the hype, which is good, but it's also bad, because hype creates expectations that sometimes can be very unrealistic. So Gardner believes that we are reaching the peak of inflated expectations with quantum computing, which is then followed by the trough of disillusionment, where most people will just give up. All right, conclusion. We might have disagreements about whether the time is right. By the time is right here, I mean whether it's a good time to try to start a business or not. And that's fine. I think that's fair. But at the same time, I also believe there's a very exciting time to be in the field. It's amazing, whether you're working in academia or on the business side of things. From the business side, we have really concrete opportunities. Maybe you can go and work for IBM. There's very few people who understand and work on quantum computing. And the big tech giants need people like that. So this is a real opportunity. There's the opportunity for crosstalk between disciplines. There is also real interest, as I mentioned before, people who work on molecular biology, they really need computing power. They love these ideas, but they don't know so much, so we need to go and talk to them. And also, this heuristic approach to quantum computing, just try things, which is what kind of happened with machine learning, and really help it to push it out of the winter the machine learning was before the last 15 years. From the academic side, well, I guess it's pretty clear we still have a lot of fundamental scientific questions to answer, so there's also a good opportunity there. And with that, I conclude. Thank you very much.